Forward osmosis is the physical process that occurs when two different solutions contact opposite sides of a semi-permeable membrane. A net movement of water occurs across the membrane, driven by a difference in osmotic pressure. A selectively permeable membrane allows the passage of water but rejects solute molecules and ions. The semi-permeable membranes have channels specially designed for water to pass through, while blocking the passage of other molecules. Water molecules will therefore move from one solution to another to achieve maximum mixing, and the strength of this mixing is measured by osmotic pressure. Osmotic pressure is the minimum pressure which needs to be applied to a solution to prevent the inward flow of its pure solvent across a semi-permeable membrane. It is also defined as the measure of the tendency of a solution to take in a pure solvent by osmosis. Osmotic pressure is denoted by pi. The formula to calculate osmotic pressure pi equals I, m, r, t, where pi is osmotic pressure, I is Van 't Hoff's factor, m is molar concentration of solution, r is ideal gas constant, and t is temperature in Kelvin. The diluted solutions have low osmotic pressure and high free energy, whereas concentrated solutions have high osmotic pressure and low free energy. Since water has a tendency to move toward lower energy levels, water will want to travel toward the zone of higher solute concentrations through a semi-permeable membrane. In wastewater concentration, Forward osmosis moves water from the feed solution into the draw solution. This water can then be recovered to produce clean water using a draw solution regeneration step, such as reverse osmosis. Permeate from the draw regeneration step is of high quality, as it is separated from the forward osmosis feed stream via a two-layer membrane. The purity of the permeate depends on the rejection features of the forward osmosis and reverse osmosis membrane. Depending on the characteristics of the effluent stream and the effectiveness of the entire treatment train, the extracted permeate can be reused for purposes such as cooling, rinsing, or even irrigation and drinking water. There is a separation membrane made of a protein that is available for transporting water in all living cells, which allows the passage of water from the feed, while unwanted compounds are rejected by means of the osmotic pressure difference between both sides of the membrane. The wastewater gets concentrated while the draw solution gets diluted with the extracted clean water. A recovery system then separates the clean water from the draw solution, then the draw solution again passes through the chamber. The recovery clean water can be reused, while the concentrated and reduced volume of wastewater can be disposed of and sent to waste management. Forward osmosis uses an osmotic pressure gradient to induce a net flow of water from the solution feed, low salt concentration solution, into the draw solution, higher salt concentration solution, through a semi-permeable membrane. The osmotic pressure can then be converted into a hydraulic pressure used to run a Pelton turbine and generate electricity continually regardless of weather conditions, and no pollutants are produced, which makes them reliable sources of green electricity.
Osmotic power is based on the natural phenomenon osmosis, where water moves through a semi-permeable membrane from water with a low concentration of salts to one with a high concentration. When fresh water and salt water collide, for example at the mouth of a river, an enormous amount of energy is unleashed as the waters of different salinity combine into a state of less ordered, uniform salinity. The mixing generates a significant 2.2 kilojoules of energy per litre of fresh water. Osmotic power stations recreate and harness this process by separating a tank of fresh water and a tank of salt water with a semi-permeable membrane. This membrane allows fresh water to pass while remaining impermeable to salts, so the fresh water is drawn through the membrane into the saltwater side, equalising the difference in salinity and raising the pressure in the saltwater tank. That huge pressure, the equivalent of a 120-metre water column, drives a conventional power turbine. It's estimated that a large osmotic power station could produce enough clean energy to run 30,000 European homes. Small osmotic power stations could be integrated into the basements of buildings, generating power for the surrounding district. A small experimental osmotic power station has already been built at Tofte in Norway, successfully creating 10 kilowatts of electricity.